In this video, we're going to use laws of probability to solve probability problems, and then we're also going to use it to determine whether or not two events are independent. So to begin with, we're going to look at the addition rule, or addition law. So for two events A and B, the union of them is the sum of each individual probability minus the overlap. Because when I take two individual events and I look at their overlap, I'm finding all of A, and then I'm finding all of B. So I'm adding those together, which means in the end, I end up adding this intersection twice. I can only add it once. So that's where you have to take away that intersection. So probability of either A or B occurring is the sum of each of the individual probabilities, subtracting the probability of both of those occurring, which is that intersection piece. So just a quick little practice with this, knowing my information. Here's my rule. So the probability of A plus the probability of B minus the intersection is going to equal the probability of A union B. So they're giving me A, so 0.6. They're giving me not B, they're not giving me B, I should say. The overlap is 0.3, and then the union of them is 0.7. So 0.6 plus a negative 0.3 is 0.3 subtracted over. Therefore, the probability of B occurring is 0.4. And you can do a quick double check, put that in there. 0.6 plus 0.4 minus 0.3 gives you the 0.7. Then we have mutually exclusive, also known as disjoint events. So if this is the case, there's not going to be any overlap. So if A and B are mutually exclusive, then there is no intersection. So that's why the intersection equals 0. So therefore, there is no subtraction in this case as there was in the past, because they do not have anything that's being counted twice. That's why it's just the probability of A plus the probability of B. So you have to look for words that say they're mutually exclusive. Those are some pretty common words that you'll hear if they do not have that intersection, that carryover. So in this example, we have a box of chocolates. There's 6 of them with hard centers, which we'll represent with H, and 12 of them with soft centers, which are S. So either they're hard centers or they're soft centers. They can't be both, which is why this, part A, says, are they mutually exclusive? Absolutely. So because of that, I can find the probability of each of them individually, the part over the whole. So hard candy ends up being, or hard center I should say, is 1/3. Soft center, the probability of that's 2/3. They're either hard or they're soft. Their intersection is none. They do not have anything in common. If I were to put all of those different possibilities together, my probability is 1. It's certain to occur. Then we start looking at conditional probability. You saw an example of this early on. If we have two events A and B, then A bar B is used to represent that A occurs, knowing that B has happened. So B has to happen, and then we find the probability of A based on that. When you read it, it says A given B. That's what that bar means. So in a class of 25 students, 14 like pizza, 16 like iced coffee, 1 student's like neither, and 6 like both. 1 student is randomly selected from the class. What's the probability of that, etc. First thing I would be doing is drawing myself a picture. Venn diagrams are going to be really, really helpful to try to organize your information, because then I can exclude pieces of information as it tells me. So I'll do pizza on the left and I'll do my iced coffee on the right. First thing I'm going to look for is the overlap if I can find it, and then I'll also look for the outside piece where it's none of them. So it says 1 student likes neither and 6 students like both. So both is going to be inside, neither is on the outside. 14 of them like pizza. I've already included the 6 that like pizza, therefore I have 8 left that like pizza. And 16 like iced coffee. I've already included 6 of them in the middle, so therefore 10 of them still like iced coffee. So here it says how many like pizza. I'm not saying, hey, based on this information, I'm just asking how many like pizza. So the probability of that is 14 out of 25, the part over the whole. The second part is the given statement. They like pizza given that she likes iced coffee. So you have to figure out how many of them like iced coffee. 16 of them like iced coffee. So within these 16 who like iced coffee, that's my whole that I get a look at. Now I have to figure out how many of them like pizza. That's the 6. So 6 out of 16. So therefore when I simplify this, I get a 3/8 probability. for liking pizza given the fact that they like iced coffee. Moving on, then, we start talking about a little bit more with our formulas with conditional probabilities. These are going to be found in your packet. If A and B are events that probability of A given B equals the probability of their intersection divided by the probability that B will occur. Therefore, I can multiply both sides, and instead of A given B, I can do B given A, dividing by its probability of A. So these two nicely follow suit. So based on these formulas, I'll be using different pieces of information. It is important for you to realize that this is conditional probability. This is that given statement. So take a moment, read the problem, and I would start by writing out a Venn diagram. So in this part, the easiest thing to set up is the two that dislike both of these fruits. So of the 40 students, 2 of them dislike fruit, these 2 fruits at least. So I'm left with 38 students. So if I have 38 students and I have 34 of them liking bananas, 34 like bananas, which means only 4 of them are going to just like pineapple. So if that's the case, then I have to look the other direction as well. 22 of them like pineapple. Well, I've already said 4 of them like pineapple. So the rest of them must like both, which makes 18 of them like both, which in turn means that those who like bananas are 16. So you have to think a little bit ahead, figuring out what part goes in which Venn diagram. But once you have this, you can then find the probabilities that a student likes both fruits. So I have to figure out now the probability that the student likes both of them. 18 over 40, which then simplifies to 9/20. Likes at least one fruit. So if they like at least one fruit, when I add those up, I get 20, 38 out of 40. They're both divisible by 2, so I get 19/20. Next is a given statement. Likes bananas, given that he or she likes pineapple. So find how many people like pineapple. 22. 18 plus 4. And of those 22 that like pineapple, how many of them like bananas? That's 18. So that's that overlap piece. So therefore, 9/11 like bananas given that he or she likes pineapple. And then dislikes pineapple given that he or she likes bananas. So the number that like bananas are 34. They dislike pineapple. So there's 16 of them that only like bananas. So it's 16 out of 34, which simplifies then to 8/17. Continuing, we're looking at some more probabilities. Again, take a moment to read this. I'm going to give you an opportunity to make a tree diagram, and I'm going to make one as well, keeping in mind one part of your tree diagram is the top shelf of the cupboard, and the other part is going to be the bottom shelf of the cupboard. So for my tree diagram, the top shelf contains 3 cans of pumpkin soup and 2 cans of chicken soup. The bottom has 4 cans of pumpkin soup and 1 can of chicken soup. Lucas is twice as likely to take a can from the bottom as he is from the top. So he's twice as likely, so 2/3 to take from the bottom shelf compared to 1/3 on the top shelf. Now if they go to the top shelf, there's 3 cans of pumpkin soup of the 5. So there's a 3/5 chance of picking pumpkin soup, and there's a 2/5 chance of getting chicken soup. If you go to the bottom cupboard, the bottom shelf, there's 4 cans of pumpkin soup, so that's 4/5, because there's only 5 cans of soup on the bottom, and 1 can of chicken soup, 1/5. So then, determine the probability that the 1 can of soup is chicken. So if we're going to pick chicken, chicken is here, so it's going to be this route, which is 1/3 times 2/5. Or, so I'm going to add, the other option is down here, bottom shelf and chicken. 2/3 times 1/5. So when I do that, I end up getting 4/5. or 4/15, I'm sorry, for the probability of picking chicken. Then the second one was taken from the top shelf given that it's chicken. So I already found the given statement. The chicken is the given statement, so that's going to go on the bottom. Now the top part is that it was taken from the top shelf. The top shelf is the first of the green circled ones. So that is going to be my 1/3 times 2/5. And I end up getting 2/15 over 4/15. Change the division to multiplying by the reciprocal, and you end up getting a half. So the probability that the soup was taken from the top shelf, given that it's chicken, is 1/2. Okay, moving forward then into independent events. A and B are independent if and only if the probability of their intersection is the probability of A occurring times the probability that B is occurring. So when two coins are tossed, A is the event of getting 2 heads. When a dice is rolled, B is the event of getting a 5 or a 6. Show they're independent of each other. So we're going to first start with the initial piece, find the probability of A, finding the probability of B. So 2 coins are tossed. So I want to find the probability of A, and that's getting 2 heads. So the probability of the first one being heads is 1/2, and the second one being heads is still 1/2. So the probability of A occurring is 1/4. B is the event of getting a 5 or a 6. So the probability of B occurring, there's 2 of those numbers out of 6. So that's 1/3. If they are independent, then I can just multiply the 2 probabilities. So I can take the probability of A and multiply it by the probability of B, and that's going to be the same as their intersection. So 1/4 times 1/3 gives me 1/12. Now I already have this as a visual for you for the intersection. So these are all the events that can occur: heads, 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 tails, tails, heads, and tails, tails. And on my dice I can have a 1, 2, 3, 4, 5, and 6. So I want 2 heads, and I want it to be a 5 or a 6. That only happens right here, which means that's 2 occurrences out of 1, 2, 3, 4 times 1, 2, 3, 4, 5, 6 out of 24, which is 1/12. So because this is a true statement, the intersection is 1/12, and when I multiply the 2 individual probabilities together is 1/12. Therefore, these are independent events. Working a bit more with formulas, I have a couple of different probabilities: probability A, probability B, and probability of the union is P. So I'm going to be finding the probability of the union if in part A they're mutually exclusive, meaning they have no overlap, and if B they are independent, which means their intersection is just simply the product of each individual probability. So using my formulas to come up with this, I'm stating up here the union of them is P. So this unknown I'm trying to find is the probability of A, which is 1/2, plus the probability of B, which is 1/3. I have to get common denominators. So 1/2 is 3/6 plus 1/3 is 2/6. Therefore, P is 5/6. So the probability of their union is going to be 5/6. Now in this next one, this one takes a little bit more time to go through. Oh, a little too far. So in this case, first off, if I know they're independent, this is a statement I know. The probability of their intersection equals the individual products of their probability. So the only thing I know right away from the beginning, because they're independent, is the probability of A is 1/2 times the probability of B is 1/3. Therefore, the probability of their intersection is 1/6. That's not what I'm asking for in this problem, so you got to kind of think ahead. I'm looking for the union. And I know that here's my union. The probability of the union is the probability of each of them individually added together, subtracting the overlap, which is what I kind of have above. So because they're independent, I can just take each of their individual probabilities, multiply them together, that gives me the intersection. I now have enough information to find my union. So the probability of A is 1/2 plus the probability of B, which was 1/3, subtracting their intersection, which we just found is 1/6. So going through, getting common denominators, 3/6 plus 2/6 minus 1/6 is 2/3. So that's the probability of the union, which was that p-value we were trying to find. Last but not least, got a kind of tough problem for you. I'm going to give you a minute to take a look at it. I'm going to do this completely on a different screen. Try some things out. There's a lot of information you actually need to find in order to come up with this, including a few pictures you may want to draw. So pause this just for a moment, think about some of the things you might want to do some sketches along the way, and then I'll walk you through the problem. So to begin with, it starts talking about the probability of A is 2/5. So the probability of anything here inside A is 2/5. So that whole thing is 2/5. I'm going to draw a few different pictures along the way. I can't put them all together. Because I know the probability of A is 2/5, I then know the probability of its complement is 3/5, which may be a helpful piece for us along the way. Specifically because later on I'm talking about the probability of B given the complement of A. And then I also have the probability of B given A. I'm going to start looking at what I know and just start trying to figure some things out. It's going to take me a little bit to get the probability of B. So to start with, I'm going to use this fact right here. The probability of B given the complement of A is the probability of B intersecting with the complement of A all over the probability of A's complement. So I already know A's complement, and I know B given the complement of A, which means I can instantly find my intersection. So when I plug in my information, I know 1/4 equals the probability of that intersection all over the probability of the complement, which was 3/5. So I'm dividing by 3/5. So to get rid of the division, I'm going to multiply both sides by 3/5. Therefore, 3/20 equals the probability of B intersecting with the complement of A. What that means, here's A, here's B. B intersecting with the complement of A. Their intersection of the complement to A. Where they intersect is this region right here. So that region right there is 3/20. I'm going to fill that in. This is 3/20. Okay. So now I have that piece to it. So I know B intersecting with A is, the complement of A, I'm sorry, is 3/20. So that gives me part of my picture. I'm going to move this over on this side because this will be helpful in a little while. We're going to put all of these pieces together. So the next thing I'm going to do is use the other piece that they tell me up here. The probability of B given A is 1/3. So the probability of B given A is the probability of B's intersection with A divided by the probability of A. So the probability of B given A, they tell us, is 1/3. The probability of their intersection we don't know. And the probability of A occurring is 2/5. It's dividing by 2/5, so I'm going to multiply both sides by 2/5. So therefore I get 2/15 equals the probability of B intersecting with A. New diagram. A, B. I'm finding now where they intersect. These two intersect here in the middle, which makes this piece 2/15. So now I'll move this over here. So now using these pieces of information, I knew all of A was 2/5 in this first one. And now in the second one, I found the intersection of A and B. So to find just this leftover piece out here, I can find that by taking 2/5 and subtracting that 2/15, which gives me 4/15. So this part here is 4/15. I'm going to get rid of the screen inside if I can. Way we can see it a little better. Okay, and then I found already that this red part up in here was 3/20. So I know that part's 3/20. So let's see if that helps us answer our questions now, based on this bottom green. So if I want the probability of B, I want the probability, it's a different color here, of all of B. I want all of that information in there. So if I want B, I have to take 2/15 and add 3/20. When I do that, I get 17/60 when you get common denominators. So that's the first part I needed to find. Part B asked, what's the intersection of A with the complement of B? And we ended up already calculating that. That's this yellow highlighted portion down here in this bottom one, and that's just 4/15. So with this, what we just worked on is looking at all the different laws of probability to solve your probability problems. Take a look, please, at your equations, and then using those laws of probability to determine whether or not two events are independent.